So we've already seen that the arc length is given by this. We've already seen that. So the arc length here is the length from here to here, and it's given by this. Now it's quite strange in that this here is a length. It is a one-dimensional length, but yet you've got an integral somewhere in there in order to work out the length. Now when you think of an integral, you think about the area underneath the function. But yet, when you look at the arc length, it is a length, but yet it contains an integral. There is a reason for that. If you so when you think of your standard normal integral, you think about the area, a two-dimensional area underneath a function. But what's actually happening is that when you think about your normal standard integral here, what's happening is you summing up all these rectangles. So you would start with your delta x. So let's start with a random delta x. Let's just say this is your delta x here. Okay, so you would start with your delta x. So you would start with this width here, and then you would times the height here. You would times the height here. So you would start with your delta x. The minute you times with the height, then collectively this thing here represents the area of the rectangle, and then you would sum up all the rectangles. Now, if you look at the arc length, now you would start with your delta. You would start with your delta x. So you would start with your delta x here, and then you would times this thing here. The minute you times this thing here, collectively, this whole thing here represents the length. It represents the length. So hang on. Going back to this thing here, going back one step, you would start with your delta x here, and then you would times the height here. The minute you times the height, then collectively this whole thing here represents the area. Already this thing here represents the area, and then you would sum up all the rectangles. Now looking at the arc length, you would start with your width. And then you would the minute you times whatever this thing here may be, the minute you times this thing here, then collectively this thing here represents a length, a one-dimensional length. Collectively this whole thing here represents a one-dimensional length, and then you would sum up all the lengths. So that would then give you your total arc length. Now let's extend this. So you could theoretically start with your width. So you could theoretically start with your width, and then times it with something strange. Let's say you want to work out some strange zigzag thing with two loops in the middle. Okay, so if you start with your delta x, if you start with your delta x here, if you can think of a way to create this strange zigzag thing with two loops in the middle, if you can think of a way of doing that, then collectively this thing here collectively represents the zigzag thing with two loops, and then you would sum up all the zigzag thing with two loops, sum up 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 the zigzag thing with two loops. So eventually you would sum up all these weird thing here. The point is that it doesn't always have to be an area. It can be this strange thing here. So if you can think of a way of creating this zigzag thing with two loops here, you can actually jump to the integral of this weird thing with dx here from A to B. If you can be sure that for any level of if you can be sure that you can get to within any specified degree of error, then you can, well, I hope you get. I can't really explain it properly, but I hope you can accept that it doesn't always have to be an area. It can be something strange, but you can still jump to the integral because Yeah, I hope you can grasp that.